This video should hopefully help you understand the concept of the mole a little better. Now, let's think about carbon-12. This is the isotope of carbon with a total of 12 protons and neutrons combined. And if you look in the periodic table and find its atomic weight, it weighs pretty much exactly 12 AMU. One carbon atom weighs 12 AMU. It's okay, it's a little higher in the table, it's like 12.01, but that's because there's some carbon-14 isotopes up there, out there that bring the average up a little bit. But one atom of carbon-12 weighs exactly 12 AMU. Is this just a really convenient coincidence? No. We have made the atomic mass unit to be exactly that. So we've defined it to be exactly 1/12 of the mass of a carbon-12. And this way, protons and neutrons weigh 1. And that's really convenient because they are basically the smallest things we need to think about with mass most of the time. But in the real world, any visible quantity of a substance is going to weigh way too many AMU to be practical. So we might have to report a small speck of substance as weighing 5 times 10 to the 19th AMU. And you can't even say how much that is. Could you tell me that's 50 quintillion? So it would be nice to be able to not only say that one atom of carbon weighs 12 AMU, but also a heap of carbons in real life weighs 12 grams. But obviously you'd have to have exactly the right size heap with exactly the right size, exactly the right number of carbon atoms in there. And we can in this case also conveniently define the size of our massive heap to be exactly that number of carbon-12, such that our big pile does in fact weigh exactly 12 grams. And this number of atoms that's required to be in this big pile is called Avogadro's number. So now just guess how many atoms that might be. This is also the amount of gas molecules that take up 22 liters under normal atmospheric pressure. If you went really big, you might say something in the trillions, right? But it's much higher than that. You even go past quadrillion, past quintillion, up to 600 sextillion. So this is clearly a very large number. But you should repeat it to yourself. 6.02 times 10 to the 23rd. This is one of the important numbers to memorize in chemistry. And if there are this number of molecules or atoms present, we call that amount a mole. And this is in fact the Latin word for a massive heap. And a benefit of defining the mole to be the size it is, and having Avogadro's number be 6.02 times 10 to the 23rd, is so that we can find the mass of an atom or molecule in AMU and have that number be the same number of grams that a mole of that substance weighs. So what kind of unit is the mole? It measures the number of units. It could measure anything. Just like you can have a dozen eggs or donuts or waffles or whatever, you could have a mole of eggs or donuts or carbon tetrafluoride or argon. But it's important to note when you say you have 3 moles of xenon, that's only telling you the number of xenon, the number of atoms. It doesn't tell you anything about the mass or the volume or the space taken up. So how many helium atoms in a mole of helium? 6.02 times 10 to the 23rd. How many chloroform in a mole? 6.02 times 10 to the 23rd. How many water molecules in 2 moles of water? Well, 2 times 6.02 times 10 to the 23rd, so about 1.2 times 10 to the 24th. And a mole of green beans would be 6.02 times 10 to the 24th. Now, green beans being more massive by far than atoms or molecules, this would be a very large, massive heap. This would actually cover the entire world in a 14-mile deep pile of green beans. And just like green beans are bigger than atoms, some atoms are bigger than other atoms. So a mole of xenon would be much more massive than a mole of helium. Looking at these samples here, they all have exactly the same number of atoms of whatever substance is there. But clearly, a mole of some of them way more than a mole of other metals here. We can ascertain from this that atoms of lead, our Pb here, are more massive than atoms of aluminum. But all of these samples have exactly 6.02 times 10 to the 23rd atoms present. Now, if we wanted to measure out a mole of iron, how would we do that? Would we want to count the atoms? Probably not. We would probably want to figure out how much to weigh out. And we know that the Avogadro's number is defined such that the mass of an atom of iron equals the weight in grams of a mole. So we just look at the periodic table, find that the atomic mass of iron is just over 55 AMU per atom, and we can therefore measure out just over 55 grams, and that would be a mole of iron, or 6.02 times 10 to the 23rd atoms. So test yourself here. How do you do? When we say there's 60 moles of carbon dioxide, does that tell us how much it weighs? How much space it takes up? No, it just tells us how many molecules are present. How do we go from moles to molecules? Just multiply by Avogadro's number. Multiply by 6.02 times 10 to the 23rd. If you were to order a mole of biscuits, this would, drown the world in biscuits, but it would be 6.02 times 10 to the 23rd biscuits if there was a mole of them. And let's use the trick of an AMU of an atom being the same as the mass in grams of a mole here. Hydrogen is the first element in the periodic table. It weighs about 1 AMU per atom, so therefore 1 gram per mole. Alright, nitric oxide, that's NO. So when we find the mass of a molecule, we add the masses of the two atoms. It's really handy that Avogadro's number is set such that we can say that a mole of it weighs 30 grams. And then I got a little joke for you here. How many people can you feed with guacamole? Well, Avogadro's number, of course. Now let's shift gears from moles to molarity. It is true that moles are involved in the unit of molarity, but molarity is a concentration. Molarity measures concentration, not number. Molarity is amount per volume. So from this slide we can take 3 ways to indicate molarity. One, would you be comfortable writing mole over liter to indicate molarity? Would you be comfortable putting brackets around the solutes to indicate molarity of the substance in the brackets? And would you be comfortable writing lowercase m to represent molarity? I hope not. Lowercase m means molality, which we'll see next semester. Make sure it's an uppercase m if you're trying to represent molarity. Alright, so the number of moles present and the molarity aren't necessarily very correlated. So for example, how could you have very high molarity with only a few moles present? Well, imagine you have a very concentrated saturated solution, and then you just take a very tiny fraction of a droplet of that solution. It still has the same concentration, it has the same molarity, but there is very, very few moles present in that droplet. In this example, I'm going to show you how to avoid 3 common mistakes when calculating molarity. It is true that molarity is amount per volume, but we can't just plug in 20 grams divided by some number of milliliters here. It's specifically moles per volume, so we have to convert grams to mole here. We know that sodium hydroxide, if we add up the masses of the atoms, is 40 AMU, or 40 grams per mole. 20 grams is half of that, so we have half of a mole. And then the second possible mistake you might make is to use the volume of solvent, in this case it would be water, instead of solution. It's specifically the volume of solution, so we'd have to use 200 milliliters here. But we shouldn't use 200 because the unit is very important. It's specifically moles per liter. So we have to convert to liters. We move the decimal point 3 places. And dividing by 0.2 is like multiplying by 5. And we get a 2.5 molar solution.